There is a telescope drifting through space right now, roughly 1 million miles from Earth, and it has been quietly dismantling everything we thought we knew about the universe. It is called the James Webb Space Telescope. When scientists designed it, launched it, and pointed it toward the ancient light at the farthest edges of the observable cosmos, they expected it to confirm what decades of careful theory had predicted. Instead, it handed the scientific community a series of discoveries so unexpected, so inconsistent with established models, that researchers across every field of astrophysics are still working out what to do with them. Galaxies that had no right to exist at the ages where Webb found them. Black holes too massive to have grown in the time available. Chemistry too complex to have appeared so early. Cosmic structures so organized and mature, they look nothing like the chaos the models predicted. And at the absolute edge of the telescope's deepest images, an object so strange that science does not yet have a category for it. Each discovery taken alone might be explained away. A calibration error, an edge case, a model parameter needing adjustment. Scientists applied exactly that skepticism, rigorously and patiently. But these findings did not arrive scattered and isolated. They came together from the same instrument, within the same years, all pointing in the same direction. When anomalies cluster rather than scatter, that is not noise, that is signal. This is the story of what James Webb has actually found, what it means for the most successful theory of the cosmos ever constructed, and why the universe we actually live in appears to be something genuinely different from the one we thought we understood. Every great telescope is built to answer a foundational question. For Webb, that question was deceptively simple. What did the very first galaxies look like, and how did they form? The question sounds clean. The answer turned out to be anything but. Before Webb opened its golden mirror to the sky, the scientific community had a detailed and internally consistent picture of what to expect. That picture had been refined over decades, validated against independent observations, and confirmed by thousands of computer simulations run on the world's most powerful machines. According to that picture, the universe in its first few 100 million years was a chaotic and violent place. Tiny density fluctuations from the Big Bang, just 1 part in 100,000, had to be slowly amplified by gravity across enormous timescales before anything resembling a galaxy could emerge. The first structures should have been small, irregular, and dim. Large, bright, organized galaxies were a late development, the product of billions of years of gradual merging and growth. Small structures come first, large ones come later. This was not a preliminary guess. It was the established prediction of the most thoroughly tested cosmological model in history. Webb pointed at a patch of sky so small that a grain of sand held at arm's length would cover it completely. In that sliver of space, it found hundreds of ancient galaxies from the earliest epoch of cosmic history. That alone would have been extraordinary. Then the research teams began measuring those galaxies in detail, and the room went quiet. Some of them were massive, not small and irregular. Massive. Fully formed, structurally coherent, radiantly bright systems sitting in a period of time when, according to every model ever built, they had absolutely no right to be there. One early candidate appeared to contain as many stars as the Milky Way, inside a universe only a few 100 million years old. Our own galaxy took billions of years to reach its current size. This object appeared to have done it in a fraction of that time. Astronomer Garth Illingworth, involved in early Webb analysis, described the findings with unusual bluntness. The galaxies looked fully formed at a point when the universe had only been running for a cosmic equivalent of a few minutes. To understand why this is alarming, consider how galaxies are actually measured. Astronomers do not count individual stars across billions of light years. They measure total light output and calculate stellar mass, a technique cross-validated across thousands of galaxies. When teams applied it to Webb's extreme early targets, a team from the University of Melbourne put the core problem plainly. These galaxies appeared to have converted nearly all of their available gas into stars, with an efficiency that current physics says is impossible. Normal galaxy formation converts roughly 10% of available gas into stars across billions of years. These objects appeared to have converted 80 to 100% in a fraction of that time. Researchers tried every available explanation: calibration, errors, eliminated after months of review, active black holes inflating brightness estimates. Some objects showed nuclear activity, but many showed pure stellar light, and the black holes required would themselves be equally impossible for their age. Incorrect redshift measurements. For the most extreme cases, the distances have since been confirmed spectroscopically, wavelength by wavelength. The galaxies are where Webb says they are. Think of it this way: finding a single brick at a construction site on the morning the foundation was poured, versus finding a completed 40-story building. For decades, the standard framework of cosmology, lambda cold dark matter, or LCDM, did not merely work. It worked beautifully. It predicted the specific temperature patterns of the oldest light in the universe, the abundance of the lightest chemical elements forged in the first minutes after the Big Bang, and the large-scale arrangement of galaxies across cosmic time. Cosmologists trusted it the way engineers trust thermodynamics. Webb handed it a failure it cannot easily absorb, and the failure is not in a corner of the model. It is in the timeline itself. Lambda CDM predicts that gravity had to work slowly, amplifying tiny density variations in the smooth early universe across hundreds of millions to billions of years before large, organized structures could emerge. The simulations that model this process have been run thousands of times and consistently produce the same result. Massive, structured galaxies are a late development. When a team of astrophysicists ran a direct comparison, taking the most extreme early galaxies Webb identified and measuring them against the best available simulations, the result was a discrepancy of roughly a factor of 100 in expected stellar mass. The observed galaxies were up to 100 times more massive than anything the simulations predicted at that cosmic age. 100 times. That is not a minor discrepancy requiring a parameter adjustment. It is a fundamental conflict. The scientific community's response was methodical. Systematic measurement error was ruled out after months of calibration review. Active galactic nuclei inflating brightness estimates were partially applicable, but the black holes required would themselves be equally impossible for their age. Dust correction adjustments helped modestly for some objects, but setting dust to zero entirely did not resolve the most extreme cases. The statistical fluke argument that Webb accidentally pointed at an unusually overdense patch of early universe collapsed when other teams pointed the telescope at different patches of sky and found the same thing. Some researchers are now seriously exploring whether dark matter itself may have behaved differently in the early universe than current theory assumes. The difficulty is that modifying dark matter's behavior to accommodate faster early galaxy formation tends to disrupt the model's predictions for later cosmic epochs we can test directly, and those predictions currently match observations reasonably well. Every proposed fix introduces new complications elsewhere. That is the hallmark of a model under genuine structural stress. Dark matter is the universe's most important invisible ingredient. It emits no light, reflects no light, and absorbs no light. The only reason scientists are confident it exists is what it does to everything around it. It bends light from distant galaxies through gravitational lensing, holds galaxy clusters together that would otherwise fly apart, and provides the cosmic scaffolding along which visible matter arranges itself into the structures we observe. For 4 decades, the standard model treated dark matter as cold, slow-moving, interacting with ordinary matter only through gravity, and clustering in predictable ways that drove structure formation at a predictable rate. Simulations built on this assumption matched observations with remarkable accuracy. Webb has introduced a complication the model cannot quietly absorb. Several independent research groups compared Webb's early galaxy observations against the most sophisticated, cold dark matter simulations available. The simulations consistently and significantly underproduced massive, organized galaxies in the early universe. Something in the behavior of this invisible scaffolding was allowing visible matter to organize itself faster than any simulation allowed. One serious proposal gaining attention is that dark matter in the early universe may have behaved less like a collection of slow-moving particles and more like a quantum wave distributed across cosmic scales, sometimes called fuzzy dark matter or ultralight axon dark matter. On small scales, this model predicts smooth quantum cores rather than the dense, spiky clumps that conventional dark matter produces, potentially allowing faster early galaxy assembly in ways that align better with Webb's observations. The difficulty is that this modification creates new tensions elsewhere, particularly in predictions for the number of small satellite galaxies orbiting larger ones. Account that observations match reasonably well under the conventional picture. Solving one problem by relocating it is not a solution. What makes Webb's contribution uniquely powerful here is precision. Every deep field image adds data on the thickness and distribution of cosmic filaments, the density of galaxy cluster nodes, and the size of the voids between them, all of which encode information about dark matter's physical properties. The early results from these analyses are not relieving the tension. The filaments appear smoother and more uniformly distributed than standard simulations predict. The nodes are denser. The large-scale topology of the early universe looks measurably different from what any conventional dark matter model produces. Chaos was supposed to define the early universe. When cosmologists modeled what the first galaxies would look like in detail, not just their masses, but their actual shapes, the picture they arrived at was one of turbulence and disorder. Gas crashing in from every direction simultaneously, continuous collisions between proto-galactic fragments, stellar populations of wildly different ages jumbled together in irregular asymmetric structures. The early universe was a construction zone mid-explosion, and its galaxies were expected to look exactly that way. Webb looked at galaxies from the first billion years of cosmic history and found something that genuinely surprised every research team that examined the images. Some of those ancient galaxies looked calm, structured, disk-shaped, rotating. A disk galaxy requires stability to form. The flat, organized rotating structure that defines objects like the Milky Way or Andromeda only develops when a galaxy has had enough time to settle, when violent inflows and collisions have calmed down enough for organized rotation to dominate. The standard model placed disk galaxies firmly in the category of late cosmic developments. Webb found them at 700 million years after the Big Bang, an epoch when the model predicted constant mergers and continuous bombardment from infalling material should have disrupted disk formation repeatedly, leaving the galaxy population dominated by irregular and disturbed shapes. The telescope saw order where the model expected chaos. Two explanations are under active investigation. The first is that gas arrived along organized channels, cold streams flowing along cosmic filaments that naturally imparted rotation rather than disrupting it. This idea had been proposed theoretically for years. Webb's imaging is providing the first direct visual evidence it actually operated at cosmic scales. The second connects back to the dark matter scaffolding problem. If early galactic halos were smoother and less merger-prone than cold dark matter predicts, the environment inside them would have been calmer, enabling disk formation to proceed earlier and more efficiently. The two anomalies reinforce each other. Unexpected disk structures and unexpected halo behavior point toward the same underlying revision. The early universe was a more ordered place than the standard model described, and a disk-shaped galaxy sustains star formation continuously across its full extent, far more efficiently than a chaotic irregular one, which directly helps explain how these ancient galaxies accumulated such enormous stellar masses so quickly. At the center of nearly every large galaxy in the observable universe sits a supermassive black hole. Our own Milky Way hosts one carrying a mass equivalent to 4 million times that of our Sun. These objects are standard features of the galactic universe, but their existence at the scales we observe raises one of the most difficult unsolved problems in astrophysics. How did they get so large? A black hole forms when a massive star exhausts its fuel and collapses. These stellar mass objects typically carry masses of a few to a few dozen times that of our Sun, modest by galactic standards. To grow from that starting point to the supermassive scale observed at galactic centers, a black hole must consume material steadily and continuously, governed by a hard physical ceiling. The Eddington limit, above a certain feeding rate, radiation pressure from superheated infalling material blows away the surrounding gas, cutting off the supply. Growing even to a few 100 million solar masses requires at minimum roughly 1 billion years of essentially uninterrupted near maximum feeding. Webb found ancient black holes already sitting at billions of solar masses inside galaxies that existed when the universe was less than 1 billion years old. One widely discussed case involves a quasar detected at a point in cosmic history, roughly 700 million years after the Big Bang. The black hole powering it appears to carry approximately 1.6 billion solar masses. At that cosmic age, standard calculations, there has simply not been enough time for anything to grow that large from any known starting point. The numbers do not close. The timeline does not fit. This is not an isolated case. Webb identified multiple examples, each pressing harder against the limits of what standard formation physics permits. Proposed solutions include the direct collapse of massive early gas clouds into black hole-like objects without a stellar phase, potentially providing a head start of 100,000 solar masses or more. The problem is that the conditions required for direct collapse are very specific, and producing enough of these events to explain the full observed population stretches the available initial conditions considerably. Another proposal involves mergers of smaller objects in dense early star clusters, but these environments are themselves difficult to explain without creating new conflicts with galaxy formation models. A third idea involves brief periods of super Eddington feeding, temporarily exceeding the nominal limit through specific geometric arrangements of infalling gas and outgoing jets. There is evidence this occurs in some nearby galaxies. Whether it can sustain long enough to build the most extreme early cases Webb has found remains deeply debated, but the sheer size of these objects is only half the problem. The other half involves their relationship to the galaxies surrounding them. In the standard picture, central black holes are passengers. The galaxy forms first from collapsing gas clouds, stars ignite, structure develops, and eventually the central black hole grows at the galaxy's core, fed by gas channeled inward as the galaxy matures. This sequence was supported by a striking observational regularity found across thousands of nearby galaxies. The central black hole mass is almost always approximately 0.1% of the surrounding galaxy's total stellar mass. Galaxy first, black hole second. Webb shattered that picture. In several of its early universe detections, the central black hole accounts for a far larger fraction of host galaxy mass than the nearby universe ratio predicts, in some extreme cases, roughly comparable to all the surrounding stars combined. The central engine is not a tiny passenger. It looks like the dominant feature. This forces a deeply uncomfortable choice. Either the black hole formed first, and the galaxy assembled itself around it, or the black hole grew far faster than its surrounding galaxy, in a way that current theory cannot cleanly provide. If the first option is correct, these ancient central engines were not products of galaxy evolution. They were drivers of it, their gravitational influence and radiation shaping how and where the surrounding galaxy's stars formed, acting not as passengers, but as architects. Step back far enough from any galaxy or cluster, and the universe reveals a structure on a scale that strains the imagination. Galaxies do not scatter randomly through space. They collect along enormous thin filaments of gas and invisible matter stretching across hundreds of millions of light years, forming the boundaries of vast, nearly empty regions called voids. Where filaments cross, galaxy clusters concentrate. Where nodes connect along multiple filaments, superclusters accumulate. This three-dimensional arrangement, filaments, nodes, and voids interlocked across cosmic scales, is called the cosmic web, and it is the largest known organized structure in the universe. Previous telescopes could only infer the cosmic web's existence through statistical analysis. Webb now images sections of it directly, capturing the filaments as visible structures. Chains of galaxies aligned along cosmic threads, tracing the paths of invisible dark matter beneath them. When researchers compared the mathematical structure of the cosmic web with the structure of the human brain's neural network as mapped by electron microscopy, the quantitative similarity was striking enough to merit peer-reviewed publication. Both networks carry roughly the same fraction of their mass in nodes versus filaments, and both show similar small world connectivity properties. The researchers were explicit. This is not a causal connection. It reflects universal organizing principles. Gravity concentrating matter into nodes while cosmic expansion distributes it along filaments, mirroring mathematically the branching geometries that govern neural growth. Webb's precise imaging of cosmic web structure is now being used to test dark matter distribution models directly. The filaments appear smoother than standard simulations predict. The nodes are denser. The large-scale topology of the early universe looks different from what conventional models produce, adding to the tension already identified in galaxy formation, not resolving it. Building molecular complexity in space requires specific ingredients and conditions. You need heavier elements, carbon, oxygen, nitrogen, which can only be created inside stars and released when those stars die. You need time for those elements to spread, cool, and undergo the chemical reactions that produce molecular structures. And you need environments stable enough that fragile molecules can survive without being torn apart by intense radiation. The early universe had essentially none of those conditions. It was hot, radiation-drenched, chemically primitive, and violent. The first few 100 million years of cosmic history should have been a near-total desert for complex chemistry. Webb found water vapor in stellar nurseries embedded in galaxies whose light left before the universe was 1 billion years old. The detection is not in dispute. Multiple independent teams verified the spectroscopic signatures. The debate is how it got there so quickly. Producing water in space requires oxygen, which can only be forged inside stars and released when they die in supernovae. For oxygen to reach concentrations sufficient to produce detectable water in a stellar nursery, at least one full generation of massive stars must have already formed, lived, and died in that region. At the distances Webb is probing, the time available for that entire process is uncomfortably tight, pressing right at the upper limits of what chemical evolution models allow under the most optimistic assumptions. The organic molecule detections are more provocative still. Carbon-bearing molecules of moderate complexity, chemical precursors to the building blocks of biochemistry, were detected in these ancient stellar nurseries. Finding them this early means the molecular pathways that eventually lead toward amino acids and nucleotides were developing billions of years earlier than the standard timeline predicted, and across far more locations simultaneously. A universe chemically primed for complexity this early is a universe that has had more time and more opportunities to develop that complexity than we calculated. The oldest light in the universe is the cosmic microwave background, the faint thermal glow left over from roughly 380,000 years after the Big Bang, when the cosmos first cooled enough for hydrogen atoms to form and light could travel freely. That ancient light now arrives from every direction in the sky with extraordinary uniformity, its temperature varying across the entire visible sky by only about 1 part in 100,000. But the map of that light carries one feature that resists any clean explanation. Roughly in the direction of the constellation Eridanus sits a region substantially colder than its surroundings. A cold spot spanning an area about 8 times the angular diameter of the full moon, with a temperature drop measurably below the average background. Statistical analyses consistently find that a cold spot of this size and prominence has a probability of arising purely by chance of less than 1%. It is almost certainly real. What created it remains contested. The conventional explanation is that a supervoid, an enormous region of space containing far less matter than average, sits in the foreground, imprinting a cold signature on ancient background light as photons travel through it and undergo a specific energy exchange related to cosmic expansion. Galaxy surveys in that direction have identified a real large-scale void. The problem is that researchers have concluded this void is probably not large enough or empty enough to fully account for the temperature anomaly. Something additional may be contributing. The more provocative explanation, proposed seriously by physicists working within established inflationary cosmology, not by fringe theorists, is that the cold spot is a physical scar from a collision between our universe and a neighboring bubble universe during the inflationary epoch. Inflationary cosmology predicts that bubble universes form continuously within an eternally inflating background. If 2 bubbles intersected during inflation, the collision would deposit energy in a specific geometric pattern, and the cold spot's profile is roughly consistent with what some models of such a collision would produce. Webb's contribution here is indirect but real. Its deep field observations in and around the cold spot are being used to map the matter distribution in that direction with unprecedented precision, potentially isolating how much of the temperature anomaly comes from the foreground void versus from something that happened in the first fractions of a second of cosmic history. The standard cosmological model places the age of the universe at approximately 13.8 billion years. The oldest confirmed stars in the Milky Way carry estimated ages of roughly 13 to 14 billion years. The margin between those numbers is already thin. Webb is making it thinner. The telescope has been producing increasingly precise measurements of stellar populations inside ancient globular clusters. Several recent analyses have pushed stellar age estimates toward the higher end of existing uncertainty ranges, clustering closer to 14 billion years than previous measurements suggested. A universe 13.8 billion years old containing stars aged 14 billion years is technically impossible, and even if the numbers do not quite cross that line, the oldest stars pressing this close to the age of the universe leaves no room for the physical processes that must precede star formation: cooling, gravitational clumping, gas collapse. That chain requires hundreds of millions of years at minimum. This connects directly to a crisis that predates Webb, but that the telescope has amplified considerably. 2 completely independent methods of measuring the universe's expansion rate give answers that refuse to agree. Analyzing the cosmic microwave background yields approximately 67 kilometers per second per megaparsec, a chain of distance measurements built on pulsating variable stars and stellar explosions, measuring how fast nearby galaxies are receding today, consistently produces approximately 73 That gap represents a catastrophic inconsistency between two independent measurements of the same fundamental property of the universe. Webb made the situation clearer and more uncomfortable. A research team used the telescope to obtain highly precise measurements of the variable stars that anchor the local distance scale, dramatically shrinking the uncertainties that had been the leading candidate explanation for the disagreement. The local measurement remained stubbornly high. The error bars had shrunk, the tension had not. Webb effectively eliminated the most convenient escape route. What remains as possible explanations? A systematic error in one measurement chain that years of intense scrutiny have failed to identify, or a fundamental gap in the Standard Model's account of how the universe has expanded across its full history. The second possibility would require revising our understanding of dark energy itself. In 2024, that revision was directly prompted by data. A massive galaxy survey mapping tens of millions of galaxies across cosmic history, combined with Webb's precision observations, produced a statistically significant result. The expansion history best fit by the combined data was inconsistent with a perfectly constant dark energy. The data preferred a scenario in which dark energy was stronger in the past and is weakening over time, a dynamic, evolving force rather than the fixed cosmological constant that has anchored the Standard Model for 25 years. If dark energy is genuinely weakening, the predicted future of the universe changes entirely. Under a constant dark energy, the cosmos expands forever into cold darkness. Under a weakening one, the future is genuinely open. The expansion could slow, stabilize, or reverse. The universe might eventually contract. The 2024 data was not sufficient to determine which trajectory is correct. It was sufficient to suggest, with meaningful statistical weight, that the trajectory is not the one the Standard Model has been assuming. Step back from the individual findings and look at them together. Galaxies too massive for their age. Central black holes too large for any known formation mechanism to have built in the time available. A cosmic timeline that strains under the weight of what the data actually shows. Dark matter scaffolding behaving differently than every simulation predicts. Complex chemistry appearing billions of years earlier than chemical evolution models allow. Disk galaxies forming in conditions that should have made them impossible. Two independent measurements of the universe's expansion rate arriving at fundamentally incompatible answers. The oldest known stars pressing uncomfortably close to the age of the universe itself. Dark energy that may be evolving rather than constant. And at the absolute edge of Webb's deepest long exposures, an object producing spectral signatures that do not match any known category. Not a galaxy, not a quasar, not any stellar class that could produce confusion in the data. Something science has not yet named. Every one of these findings, examined in isolation, could reasonably be attributed to a measurement anomaly, an edge case, or a model parameter requiring adjustment. Scientists know this. They apply exactly that caution, and they should, but the findings are not in isolation. They arrived simultaneously, from the same instrument, within the same years of operation, all describing the same basic divergence. The universe is more structurally organized in its earliest phase, more chemically complex far earlier in cosmic time, more energetically extreme, and assembled itself faster than any framework built on the Standard Model was ever designed to accommodate. When anomalies scatter randomly, they describe measurement noise. When they cluster, reinforcing each other, describing a coherent picture, pointing consistently in the same direction, they describe something else entirely. That is signal. The James Webb Space Telescope launched as a scientific instrument. It has become something considerably more significant, the device through which humanity is renegotiating its understanding of what the universe fundamentally is, how old it is, how it assembled itself, what forces have governed its evolution, how it will eventually end, and whether, Somewhere in all of that vast observed space, it contains structures and histories beyond our own. The golden mirror is still open. The data is still arriving. Whatever Webb finds next will change the frame again, as it has changed it consistently since its first images reached the scientific community. There is a before and an after in the history of cosmology. We are living in the after, and the universe, patient and vast beyond meaningful comparison, full of secrets older than anything we have adequate words for, is only just beginning to answer.